Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be continuing Chapter 11 on Logistic Regression, and we'll be looking at an example which has both a continuous and categorical predictor variable in the model. So we look back again to a data set that's rather old, 1965, but an interesting data set and one that still applies today for people with leukemia, which is of different white blood cell types. So two researchers reported on the survival time in weeks. So once you've been diagnosed, how long do you survive after you've been diagnosed with this with leukemia? And so we have their survival time in weeks as the response variable, which we're going to dichotomize into a binary variable. And we have their white blood cell count, WBC, and we also have whether each person was classified as being AG positive or AG negative, which is an indication of a certain morphological characteristic of the white cells. Okay, so we've got the count of the cells and then these morphological or shape characteristic. So we are going to code the binary factor indicator variable as a 0 if it was AG negative and a 1 if it's AG positive. And for every category for the number of cells, okay, which you could imagine may not be the same for very many people, and the status, AG status, will have the number of patients there. And here's the citation for this data set if you want to look it up. I think they actually fit a different model than we're going to fit, but not a big deal. Oh, that's not true. That's a different data set. One coming up. All right, so here's the leukemia data set. If we read it in here, see what we start with. We have so for each person we have the number total in that group, and most of these are going to be 1. There's only a couple cases that has more than 1 in that category. There's 1 there and there's the last one. And basically that's because these values of 10,000, that's basically the maximum that the machine can register for the white blood cell count. So that's why you can actually get multiple observations at that white blood cell count. Otherwise, each individual has a unique white blood cell count. So here we have the total number in that group 1. NRES, let's go back to the example here. That's the number surviving at least 1 year. Okay. And then we have AG status, either 0 or 1. So here's some zeros down here, and there's a 1, and then the white blood cell count. So those are our original 4 columns. To that, we're going to make the AG status a factor variable. We're also going to look at the log of the white blood cell count, because you can see sort of the growth here, sort of almost powers of 10 happening. So taking the log will be helpful here. I happen to take the natural log, but log base 10 would be just fine as well. And then we're also going to give the observed proportion p hat observed of the survivors of at least 1 year survival, right? At least 1 year, yes. So number NRES divided by n total. And so finally, this is our data set. We've got the factor variable that we needed, and we have p hat and the log of the white blood cell count. So there's the table. You can see now the p hats, we've got tons of 1s, we have this 1/3, and then tons of 0s. And so we're not going to get this beautiful straight line relationship on the logit scale anymore. All right, so our goal is to fit or estimate these betas, beta 1 and beta 2. This is a continuous variable for the log of the white blood cell count, and AG is the AG status. And just as in multiple regression, we can write, because we've got AG status, we're going to have an indicator variable here. You know, if AG is 0, that means negative. AG is 1 is positive. So our baseline group is AG negative individuals. And so that AG value here will be 0. And so you can write out what the regression equation is for those AG negative individuals. If I scroll down a little bit, for AG positive, then it's going to equal 1. And so now we've got beta naught and beta 1 that can be added together. So we have different intercepts, but the same slope. That's the assumption in this regression model. All right, so I think we're okay with a lot of these comments here. I do recommend you to read those, however. So here on the Logit scale, this is what the regression model looks like. We've got parallel lines because it had the same slope, but we all have different intercepts, this offset. And if the indicator variable for AG being 1 was positive, then it would be a positive shift, just as we see here. And so here on the probability scale, it's hard to know exactly what parallel sigmoid curves are, but it basically represents a horizontal shift in these curves. All right, so let's go ahead and fit our regression model. So we're going to do the generalized linear model. We're going to put the number of successes and the number of failures as 2 columns as the response. We've got AG, which is the AG categorical status, and then the continuous variable log of the white blood cell count. We specify the most important part of the family is binomial from the leukemia data set. And right away I'm just going to check the residual deviance lack of fit test using the chi-square distribution. We have a large p-value of almost 0.7, so there's not any gross deficiency in our model in terms of fitting the data. Let's take a look at our walled test. This gives us the ability of testing both of these parameters at the same time. Do we need them at all? So let's ask whether both parameters equal 0. So here I'm putting in the coefficients for the linear regression, putting in the variance covariance matrix, and then here specifying which terms I'm simultaneously testing are equal to 0, and that's terms 2 and 3 because the intercept is term 1. And here this is a 2-degree of freedom test, and we have a p-value that's relatively small, so this suggests that at least one of these, so we're going to reject the null that both are equal to 0 in favor of the alternative that at least one of these is different from 0. So let's look at a summary of our fitted model. And we can see, let me scroll down enough that looking at the parameter estimate table, the intercept's not really that interesting. That's the survival time of someone who is AG negative with a white blood cell count, or log white blood cell count of 0, or equivalently a white blood cell count equal to 1 if you have 1 white blood cell. So we've got a positive number for AG, the AG status, AG positive status, which says that the survival time increases if you're AG positive. And we have a negative number for the log white blood cell count. So as the log white blood cell count increases, your survival probability decreases. And both of those are significant, conditional on the other variable being in the model. So it seems that we need both variables. Here is just as a reminder, the residual deviance that we did the lack of, or goodness of fit test on earlier. All right, so this is the same code as we saw before for calculating the fitted values. The only real differences here are that we're putting in the correct model for making the predictions, and we need to specify both columns for the predictor variables, the log white blood cell count and the AG status. But once you put that in and you use the rest of the code, I need to put in the appropriate data set, of course, leukemia, then plotting is fairly straightforward. And here is a plot of the data and the fitted values, as well as their confidence bands. So take a look at these circles. Oops, not that one. The one even above. That circle, all these circles up here. Those are all the observed proportions, where the observed proportion was equal to 1. And these are all the observed proportions that were equal to 0. Okay, so you can see that we're trying to fit zeros and ones, and these S-curves are sort of doing the best that they can. We have two colors based on the AG negative status or positive status. So negative is red, positive is blue, and p hat is the probability of survival. The horizontal axis is the log of the white blood cell count. And we see a decreasing relationship. As the log of the white blood cell count increases, the probability of survival decreases, and that there's a big offset between these two AG status curves. The curves are only going from the minimum to maximum value, which is why this red truncates where it does. And you can also see how wide this band is. We don't have that much data. We only have 33 observations or so. And so, you know, for a person with a, say, log white blood cell count of 6, like this red person here, who's AG negative, their probability of survival at least 1 year goes from about 0.5 up to about 0.6 something. So there's a wide range of uncertainty. And in fact, that's not even, yeah, okay, that's correct. All right, here's the table that plot came from. It has the same columns that we saw in the previous example. And we can take a look at the individual curves for each, or regression equations for each status group. So for AG negative status, where AG equals 0, this AG equals 0, that indicator variable, so this term doesn't go, isn't included, so we've got just that variable, or that equation. And for positive people, we have a 1, and so these two numbers, the 2.52, adds to the intercept, and that's the difference in those regression equations. And when you solve for p, these are the curves that we saw on the previous plot. Okay, so I'm going to skip, well, let me see. All right, let's finish this video by talking about odds ratios. So there's different ways to interpret these parameters, and one way is about estimating log odds of survival and differences in log odds between two groups. So if we want to ask the question, how does the log odds, so here's the log of the odds, how is that different between AG negative status people, this here, this equation, and AG positive status people, that's this equation here. Remember, the only thing that's really different is the intercept. Then we can ask that question by just taking the difference. Here's AG positive minus AG negative. It's a difference of 2.52. That was, in fact, that regression quantity associated with the AG positive value. And there's a way to interpret this based on the odds. So using the properties of the exponential functions, the odds that an AG positive patient lives at least 1 year is e to that number, 2.52, which is 12. 12 times larger than the odds of an AG negative person, regardless of what their white blood cell count is. So you definitely want to be in the AG positive group here, because your odds of surviving are 12 times better than the AG negative. So that's sort of a statement of probability, but it's on the odds scale. The odds being probability of success divided by the probability of failure. Okay. We can also calculate confidence intervals for the odds ratio. So this summary and the confidence interval for the AG odds ratio is given below. We're going to look at a few sets of output here, and let's just scroll on down to that. All right, so here is the confidence interval for the regression parameters. So let me actually page up for a moment. Remember what our regression parameters looked like. We have 2.52 for the AG and negative 1.1 for log of the white blood cell count. We also have the intercept, which often won't be very interesting. So those estimates actually fall right between these two numbers. So the AG status goes from basically 0.6 up to 5, and the log white blood cell count confidence interval goes from negative 2.2 up to negative 0.3. So we can get confidence intervals for those regression coefficients. All right, so there's another way to get confidence intervals, but I would trust the one up here. And furthermore, you can exponentiate the coefficients to get them, to interpret them as on the odds ratio scale. So notice here, I've got the odds ratios, which are the coefficients, and I have their confidence intervals over here. And if we take that whole quantity, which is inside these parentheses, and exponentiate that, then we have the estimates on the odds ratio scale. So the 12.4, which if I scroll up for a moment, we interpreted here, 12.4, that you're 12.4 times more likely to survive if you're AG positive versus negative. Page back down. That is this quantity here. Furthermore, we can interpret this quantity. So this suggests that, or this says that for every unit increase in the log white blood cell count, your odds of surviving 1 year are 0.3 what they were if you were 1 unit less in the log white blood cell count. That probably wasn't said very well. Let me try again. So say log white blood cell count was 5 and you had a certain odds of survival. If you increase that from 5 to 6, now your odds of survival are 0.3 what they were before. So that is a marked decrease. All right. So we are here fitting a model of equal slopes, but it's quite natural to add an interaction which would allow for different slopes depending on which AG status you're in. And it basically works the same way as in multiple regression, and you can determine which model you need based on the AIC values or comparing using the deviance statistic and finding that there's lack of fit with the simple parallel line, no interaction model. All right, to finish this section, I want to talk, you know what, I think I will let you read this section. So there's a little bit more here about interpreting odds ratios. I've got an example that's fairly abstract, and then there's two more examples, one that we've already discussed from the leukemia, and one that's based on being admitted to an engineering school, whether you are male or female. So we'll come back and we will look at mortality of the confused flower beetle, which will suggest adding a quadratic term to the regression equation.